ఏమంటారంటే ఈ మెషిన్ మన అక్కడ క్యాలిబ్రేషన్ తప్పు వస్తే థర్డ్ వ్యాలిడేషన్ చేసి వాళ్ళ ఇన్ఫర్మేషన్
ఇదే మనం ఎక్కడైనా ఇప్పుడు దీని పరిస్థితి మనం చెప్తున్నాము. ఇది పీడిఎఫ్ వేస్తా లేదండి. ఎవరైనా డెబిట్ చేస్తే కూడా ఈజీ ఉంటుంది. ఇదే ఇది మన రైస్ 1 కేజీలో ఇది వచ్చేసి 100 కేజీలో 1 కేజీ 100 కేజీ 1 కేజీ ఇది గవర్నమెంట్ ఆఫ్ ఇండియా ఎఫ్ఎస్ఎస్ఐ ఎక్కడైతే అప్రూవ్ చేసిందో అది చెక్ చేసుకుంటాం సార్. ఈ 3 మినరల్ ఉన్నాయని వీట్ గోల్డ్, థయామిన్ అండ్ ఐరన్ 3 ఉంటేనే మనం వీట్ గోల్డ్ సార్, వీట్ గోల్డ్, ఐరన్ అండ్ థయామిన్ ఇది మిక్స్ చేసి కొంతమంది అది బయటకు వస్తున్నప్పుడు ప్లాస్టిక్ రైస్ అని భయపడతారు. కానీ ఇది మంచి న్యూట్రిషన్. తెలుసుకోవచ్చు దీని గురించి తెలియదు. మంచి సప్లిమెంట్ 3 మినరల్స్ అనీమియా ప్రాబ్లం దీనివల్ల ఇది ఇక్కడ వెళ్ళండి ఒకసారి వెళ్ళండి. రైస్ వచ్చేయండి. ఖాళీ చేసేసి టిఫిన్ ఎవరికి వెళ్ళిపోయారు.
చాలా కన్ఫ్యూజ్ అవుతున్నారు
చేస్తారు. వాళ్ళు చేసినప్పుడు అది మిషన్ ఈ మిషన్ ఒకటే మిషన్ వేరియేషన్ ఇదే పెట్టబోతున్నాం. అన్నీ పెట్టి నేను ఇవన్నీ అరెస్ట్ చేయాలనుకుంటున్నాను. అందుకే ఫీల్డ్ వచ్చాను. 40 ఏళ్ళ రాజకీయ ఫస్ట్ టైం వస్తుంది ఇచ్చారు సార్ అందరం కూడా రైతు కుటుంబాల నుంచి వచ్చిన
ఆయన తయారు చేసి
అందుకే అన్ని స్ట్రీమ్ లైన్ చేసి సిస్టమేటిక్ వ్యవస్థ ఉండాలి. మీకు అన్యాయం జరగకూడదు, రైతుకు అన్యాయం జరగకూడదు, ఎవ్వరికి అన్యాయం జరగకూడదు అనుకున్నాను. ఐ వాంట్ స్ట్రీమ్ లైన్ ఎండ్ టు ఎండ్.
డైరెక్ట్ ఎక్స్పోర్ట్ కూడా మాకు
అది కూడా వర్కౌట్ చేస్తాను. అది కూడా మనం ఒకసారి ఎగ్జామిన్ చేసి టోటల్గా విన్ విన్ సిచ్యువేషన్లో ఈ హెరాస్మెంట్ ఎలక్షన్స్ అవుట్ ఉంటుంది. 2:2:1 అనేది ఏరియాస్ మెథడ్ చేసాం. సివిల్ సర్వీస్ కార్పొరేషన్ వీటిని ప్రపోజ్ చేసి ఇంత ఇస్తే ఇంత ఇవ్వాలి అవన్నీ పెట్టాం, మారాం. బట్ ఇవన్నీ కూడా మన సిస్టమేటిక్ అన్ని ఆలోచన చేస్తే జరగాలి. ట్రాన్స్పరెన్సీ రావాలి. ఇది కూడా ఇంకా పీరియడ్ కావాలి. సేలర్స్ కూడా పెడుతున్నాం.
ఓకేనా సార్ 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 సార్
Welcome to lecture 20. This is the NPTEL online certification course on bioreactors. In the previous two lectures, we had looked at bioreaction stoichiometry as one of the means of getting some insights into what is happening at the cell level in the bioreactor. The cells in the bioreactor are the actual factories. We worked out a problem in the previous lecture. Now let us go forward with the module itself, the module 5. We are going to begin talking about windows to the cell. Now, we said we will first consider it as a black box, the cell, and then we'll open up windows and look through the windows to see what is happening inside the cell. So, the windows to the cell are the indicators of cellular status of the cell or indicators of metabolic status of the cell. These terms, cellular status, metabolic status, energy status, and so on and so forth, redox status, and so on, these are kind of soft terms. You should not take them too strictly. These are kind of indications of what could be happening, and these are kind of common terms that are used. They are not, of course, fully understood, but they are useful. The cellular redox status is a well-known indicator, and cellular energy status is another well-known accepted indicator of the cellular or the metabolic status of the cells. The cellular redox status is typically derived from NADH. NADH, nicotinamine adenine dinucleotide, and the hydrogenated form of that. This conversion takes place in various metabolic reactions or accompanied with various metabolic reactions in the cell. NAD plus plus H plus giving you NADH. So, this has the reducing power which is taken forward for so many different important functions in the cell. So, the redox ratio, one of the ways of looking at it at least, is the ratio of NADH concentration to the total concentration of NAD plus and NADH. We have already seen that NADH fluorescence can be used to monitor the cell concentration, because the intensity of NADH fluorescence can be directly linked to cell concentration. Here it is redox ratio, the NADH divided by the total NADH pool, which consists of NAD plus and NADH. Okay, this is the redox ratio. Similarly, or in some situations, the ratio of NADH to flavin adenine dinucleotide, another important such molecule, is also taken to be the redox ratio. For energy status, it's somewhat a little more straightforward. We all know the energy is made or energy currency of the cell, ATP, adenosine triphosphate, is made by the phosphorylation of adenosine diphosphate. So, the ratio of ATP to the pool ATP plus ADP, sometimes AMP is also added here, but let us just look at these two. ATP divided by ATP plus ADP is taken to indicate the cellular energy status. So, a lot of measurements are made on these, correlated to the happenings inside the cells, correlations with respect to what is important from a bioreactor context, and efforts are made so that these indicators are varied in a particular fashion or kept constant at a particular known value to achieve desired performances by the cells in the bioreactor. So, that is one more step towards understanding what is happening at a cellular status, cellular level. Sometimes even ATP by ADP is considered the cellular energy status. There are various ways of defining this. I have just given you a couple of them. What one needs to understand is that very many metabolic processes contribute to the above. Okay, so it is not a one-to-one kind of a relationship. So many things contribute to redox status, so many things contribute to energy status. So, one needs to have some level of interpretation, or one needs to interpret this in that kind of a fuzzy fashion. It's more of an indicator. you may want to look at this paper, which has also been given in your notes as one of the papers that you would want to look at. Let me direct that to you. This is number 30, NADH culture fluorescence. The authors are Shepper, Gebar and Shugal. This is the paper for NADH culture fluorescence. The title of the paper itself is Monitoring NADH Dependent Culture Fluorescence During Cultivation on E. coli. It was published in Chemical Engineering Journal in 1987. This is something that gives you some relationship to the culture energy status. Let me, I do have a paper here. Yes. Let me briefly tell you how this is done with energy, with NADH status. To very briefly read the abstract, NADPH dependent culture fluorescence was monitored during various E. coli cultivation processes, batch and continuous cultivation in stirred tank reactors or bubble column reactors. Various strains of E. coli, including genetically modified E. coli, were used. Measurement of fluorescence signal allows biomass estimation under certain conditions, this we have already seen. The monitoring of culture fluorescence is useful for obtaining information on the metabolic status of cells. The effect of cells of different substrates, glucose and oxygen, was studied. The measurements were performed in synthetic and complex media, and the influence of the composition on of each medium was investigated. A microfluriometer was used as a routine sensor for cultivation control and provided insight into the status of cells. Okay. The what I'd like to point out is this. You see, this is biomass versus time. The points here are the individual points. Let's increase the size a little bit so that you can see it a little better. Right? Yeah. The points are experimental points and the line is given by culture fluorescence. You see a very nice relationship. This is what we talked about as a measure of the cell concentration itself. This is biomass or cell concentration in grams per liter versus time by two methods. One is by the traditional the OD method, and the other one is by the culture fluorescence method. It agrees in many situations. It doesn't agree in one such situation. This is bubble column conditions. If it is a stirred reactor, there is absolutely no problem, whereas in a bubble column there seems to be interferences which lead to a difference between these two. So one should be careful while using culture fluorescence in bubble columns. It makes sense because bubbles will interfere. And then one more thing I'll point out from this paper. Here. You see this figure? Let me blow it up a little bit if you want. Yes. This is culture fluorescence versus time. The fluorescence was at a certain level when oxygen was used, when oxygen in air was employed. Okay, let us read the figure 7 is what it just says. Okay, that doesn't matter. You have culture fluorescence at a certain level. When nitrogen is introduced, within a few seconds, the culture fluorescence goes up. The anaerobic status goes up. When nitrogen is employed, the cells become anaerobic because oxygen is no longer available as final electron acceptors, right? So the culture fluorescence at an anaerobic state is much higher than the culture fluorescence at an aerobic state, because you'll find NADH forming more. So this very clearly indicates the aerobic state of cells. When oxygen is turned back on or air is turned back on, it comes back to its original level. So this is a nice indication of what is happening inside the cell just by measuring the culture fluorescence. That's what I had talked about earlier. You can read this paper if you are interested. For the purposes of this lecture, I think this is good enough. Okay. In the case of patterns. Okay, so that is using culture fluorescence. Now, let me talk about some of our work, which was done quite a while ago, but it also is on the same lines as this. This is measurement of intracellular pH. You know, this is pH inside the cells. This is distinct from the pH of the medium. pH of the medium we know goes up and down because of acid-base additions, and we said that the pH needs to be controlled at an optimum value for best bioreactor performance and so on and so forth. We are talking of intracellular pH, pH inside the cells. Now, the pH inside the cells can somewhat be related to the energy status of the cells, because there's something called a Mitchell's hypothesis. In fact, Peter Mitchell won the Nobel Prize for this hypothesis. This essentially says that a hydrogen ion gradient across a membrane, intact membrane, is what provides the energy for ATP formation from ADP. So, in some sense, you can link the energy status of the cell to the intracellular pH level. Okay. There are some fluorescent dyes that indicate the pH through their fluorescence by getting inside the cell and so on, but we couldn't really use them because those dyes leaked out. BCECF-AM is one such dye. There's of course some detail, it might be of interest to some, so that's why I'm mentioning it briefly. These dyes could leak out, so we used a dye called 9-aminoacridine, which is a weak base whose distribution depends on the difference between the extracellular and the intracellular pH. You know, there are also these processes take place across the plasma membrane in lower organisms such as bacteria and so on. So that is what we were using. So what we did was we developed this method of intracellular pH measurement online continuously in a bioreactor, and then we used intracellular pH to grow cells at a particular intracellular pH, which is indicative of energy status, after studying that different intracellular pH levels indicate different metabolic conditions in the cell. So what we did was we measured intracellular pH through fluorescence, and we found that glucose addition, the addition of the substrate, can modify intracellular pH. So the glucose additions were done so that the intracellular pH was maintained at a certain higher level compared to the base level, so a higher energy level. And when we did that, we could reduce the anaerobic product formation by about 4-fold. So if it is anaerobic growth, then the outcomes are much less than the aerobic growth in terms of cell yield and so on. So we were able to do that much better, and we could reduce the anaerobic product yield. So these things could also be done. There are a couple of papers on intracellular pH which are given here. I would not discuss them further because of the introductory nature of this course, but if you're interested, you can look at these two papers given under 31 and know more about the intracellular pH itself. Okay, let us move forward from here. So the control, this is what I mentioned earlier. I've given this as a diagram here. Intracellular pH was controlled using fluorescence. This is not a pH probe. pH probe will measure only the pH of the medium. Then transmitted, and the controller was the one that determined the glucose feed, whether it needs to be fed, or the feed rate of glucose. So that became the manipulated variable to maintain the intracellular pH at a certain set point to reduce the anaerobic product formation. So this is the control schematic of the whole thing. Okay. So now let's start looking inside the cell through various windows, doors, and so on and so forth. I'll tell you one example of such things of looking inside the cell, and that is called metabolic flux analysis. Okay, we'll spend some time on this, the metabolic flux analysis. It's interesting. It became popular in the early 1990s. The method was known from the 70s onwards, 1970s onwards. It became popular when Valeno and Stephanopoulos published their paper on using metabolic flux analysis to provide them with directions to improve lysine production. Lysine is an amino acid that animal cells cannot make, and therefore, but that amino acid is required for a protein, so we need to supplement it through diet or other means, and therefore lysine is a huge product. Large amounts of lysine are produced annually, and therefore it's commercially a very important product. So if you improve the lysine production a little bit, then the profits could be high or the price could further be brought down, and all these made the use of metabolic flux analysis a popular one in the early 90s, and a lot of work went on for the next 20 years or about 15 years on metabolic flux analysis. We will look at the principles of metabolic flux analysis next. So as an introduction, cells make products as a result of hundreds of reactions that take place inside them. We already know this. To improve product yields, the chemical reactions of the metabolic pathways can be targeted. And let us look at a method of analysis of those pathways toward improving product yields. Okay, this is our main aim. We are going to look at a method of analysis toward improving product yields, and that method is called metabolic flux analysis, or MFA for short. To know what metabolic flux analysis is all about, let us start with this. Let us represent all the cells in culture by a single large cell to begin with. Okay, so the volume of the cell equals the volume of all the cells in the bioreactor. The remaining volume is the broth volume. This could probably be less than 10% of the, even in concentrated situations, it would be about 10 to 20%, right, of the total volume. And let us consider these set of reactions that are occurring in the cell, a hypothetical set of reactions, but these are good to understand the principles of metabolic flux analysis. SO is the substrate that's outside, that goes inside and gets converted to S through probably the reaction R0. Then S could get converted to A or B. It gets converted to A at a rate of R1. This R1 is moles per time, and it gets converted to B at the rate of R2 moles per time. B gets converted to D at the rate of 4, which comes outside. A gets converted to C at the rate of R3, which also comes outside. Okay. So this is the situation here. Let us say that this is some important metabolic pathway that is happening in the cell. This is the case. It's good to note that S, A, B are inside the cell and therefore are intracellular metabolites, whereas S, O, C and D are extracellular metabolites. And metabolite flux is a common term that is used. The term flux is very different from the engineering term flux. The engineering term flux is amount transferred per unit area perpendicular to the direction of transfer per unit time. That's a flux, right? In the case of metabolic flux, historically moles per time, or in other words a rate has been used, an amount rate has been used to indicate flux. We will continue using that because it's widely accepted in the literature. It is a rate and not flux as in engineering terms. This you need to keep in mind. So the typical units of R are 0, R1, R2 are millimole per gram cell per time. Note that it is normalized with respect to mass and not volume, right? Rather it's expressed in terms of mass, and it has not been normalized with volume. Now let us consider this large cell as a system. Let us write a balance on intracellular metabolites first. I'd like you to note that if we are writing balances on intracellular metabolites, we consider the cell as our system. This is our system, and we write the balances on the metabolites inside the cell. Let's begin with this S here. So rate of input of S minus rate of output of S, this is a system, that's what we are talking about, plus the rate of generation of S minus the rate of consumption of S equals the rate of accumulation of S. Here you need to, if S0 has come in as S0, then we consider it as transport across the system boundary. These two terms, input and output, have relevance, as you know, only when there is transport across the boundary of the system. So if S0 has become S0 here, then we can consider it as the input term. Otherwise, we consider it as a reaction term, which could be accounted for in generation or consumption. But we need to make sure that we count it only once. We cannot count it as input as well as generation, even if you want to follow a different strategy for doing this. If you follow this strategy, that if S0 becomes S0, then we consider it as transport. If S0 becomes something else inside, then it becomes a reaction. Similarly, A going to C, we are going to consider it as a reaction because A has become C. A has not become A outside. Then it can be looked at as transport. The main thing is that there should not be any double counting. So there is, if you look at that, there is no input of S into the cell. There is no output of S into the cell. That's not going anywhere. Whereas there is definitely a rate of generation and a rate of consumption. The rate of generation is R0. The rate of consumption is through these two reactions, right? Therefore, minus of R1 plus R2, that becomes minus R1 minus R2, and that equals ds dt. Similarly, for A and B, A is formed at the rate of R1, it gets converted at the rate of R2, so generation is R1, consumption is R2, R1 minus R2 is dA dt. Similarly, R2 for B formed at R2 and getting consumed at R4, therefore R2 minus R4 is dB dt. Now there is a trick here. Okay, I want you to pay some attention. We are going to consider the surroundings of the cell as a system. Okay. When we focus on extracellular metabolites, we will consider the surroundings of our cell as a system and write our balances. That's what turns out to be consistent with our approach here. So if we write a balance on the extracellular metabolites, first on S0, S0 is getting out of the system here. This is our system now. Okay, it's getting out of the system. Therefore, there is no input, but there is an output, and therefore minus R0, which comes from here, it is not being generated, it's not being consumed. So minus R0 is ds0 dt. Similarly, for D,